by Ben. Ben asked, was there a way to have the GUI print commands to the terminal? And he wants, for example, to save a shape plot. Wants to be able to do that with Python. Well, actually, there are ways to save particular windows and particular tools from the command line, and they are, I think they're done through the print and file window manager class. We can try to look that up and see, but I'd like not to get bogged down in that. There's generally, when you, if you save GUI tools to a session file, you have there's enough hook code in there that for many tools, you can figure out, you can mine those, and you can figure out what calls were used, and you can sometimes recreate things without even having to resort to hook. For example, the time axis graphs where a variable is plotted versus time. If you're unsure about the use of any of the graph methods, for example, and you'd like to be able to do something from the command line from Python, let's say, or from Hoke, without having to resort to the GUI, just go ahead and use the GUI to create a graph that looks the way you want it. Save that graph to a session file, open the session file with a plain text editor, and look at the individual graph class methods that are called. And you can then figure out what to do, what the arguments should be, and if you have to make specific changes to work under Python. So I can show you very quickly an example of how to do that right now. And then we can move on to something more substantive. Let me see here. Get everything pulled over to the side. There we go. And let me share my screen. Advanced, portion of screen, share. This is not the right portion. Where's the tool? There's the tool. Yeah, I want it up there a little bit higher. Okay, let me get Slack out of the way. So let me just do a really quick hack on this. Okay, so I'm going to just use the Neuron Demo. And let me make the text larger first. Edit preferences. Make this use a larger typeface. Select. There we go. And then close. Okay, so I'm going to do Neuron Demo just because it's a quick way to get some graphs up. And I'm going to do this. I'm going to do this release tool, which is this is a model of a presynaptic terminal, and in which there are calcium channels, and there's a pump, and there's calcium accumulation, and there's interactions between calcium and buffers, and finally transmitter is released. Okay, this is from a published article, a model done by John Moore long ago, but implemented in Neuron. Okay, so if we run a simulation, we see a lot of calcium calcium currents up here. We see free calcium concentration and calcium buffered. Got a question that just popped up. Just checking to verify that these tools have not been extended to work when extracellular mechanisms are included. I don't think so. Which tools in particular do you mean? Kelvin, why don't, if you have something to ask, why don't we just switch to regular conversation, so you can express this a little bit more clearly.
Yes, sorry, Ted. That was on Slack. I was responding to the electrotonic analysis, so that was embedded. I was just, as we were waiting here, I was catching up on some Slack messages. So I was asking about the electrotonic analysis. So we can take it up on Slack if you want. I didn't think that the tools for impedance worked with extracellular mechanisms.
The typical, no, they weren't designed to do that, and I'd have to verify that in fact they actually did work with properly with extracellular. The they should work with extracellular's default parameters, which are essentially that the extracellular layers provide no significant impediment to extracellular current flow or propagation of potential in extracellular space. The point of the tools was to be able to study the properties of individual neurons, in particular the ability to clamp areas, the ability to measure experimentally the peak EPSP amplitude, or to capture the time course of synaptic current, or even the magnitude or the total amount of current that entered into a cell over the course of synaptic activation. That kind of stuff, which ideally is done in vitro in a slice, in an experimental preparation where under conditions where extracellular space can be treated as basically a uniform potential of 0. What actually happens when there is significant extracellular resistivity is a different question. So until further notice, assume that when you're using the impedance tools, assume that the extracellular space is not presenting a significant barrier to current flow or to isopotentiality with ground. Okay.
Yeah, thanks, Ted.
Yeah, you're welcome. All right, so here we have a graph, and we might be interested in seeing, well, suppose I want to plot some variables and have them be different colors. How would, if I want to do that from the command line, so I don't have to be fooling with the GUI to create a graph, and I want to be able to show all these graphs in this way, all these plots, and maybe I even want some of the plots to have, different thicknesses. So let me do that with color brush. And how do I make the red trace be thicker than the others, for example? Okay, and how would I make the calcium pump current be not only thicker, but also dashed? So I can click on that. And now I've made these changes to the graph, and I want to see what kind of commands would be needed to do that. I'll go back to crosshair mode. So what I'm going to do is I'll use the print and file window manager to select just this graph. And you'll notice as I wiggle this, you notice in the upper left corner, you'll see that this is this outline number 9. And if I click on that, it appears off to the right-hand side here, which means it's going to be saved to a session file if I do session save selected. And I'm going to call this currents.ses. That's the file name I'm going to use. I'm going to hit return now. And so let's dive back into a terminal. I'll open a tab, and I'm back in the terminal, and let's look currents.ses. Okay, this is not a text editor. This is just exposing the individual commands. And you see some statements up here declaring object references, which is telling Hoke that these names are going to point to object instances, okay? Python doesn't require to do that because in Python, everything is an instance of some class or another. Unfortunately, this kind of syntax is necessary in Hoke. There's something that's called a list, which is a couple of lists which are being created. Here we have a statement that says, we're creating a new instance of the graph class, and we're calling it with a 0 argument. And what does it mean when you create an instance of the graph class and you're saying it in this way, okay? In Python, the equivalent in Python would be to say that save window equals h dot graph parens 0, okay? So what on earth does that mean? So let me bring up a browser and let me go to the programmer's reference and graph, and here we are. So we see under the graph class, I don't know if this needs to be bigger, but we see we could create an instance of a graph by either saying g equals h graph or g equals h graph with a 0 argument. And it says with a 0 argument, the window is not mapped, but can be sized and placed with the view function. And what does this mean, mapped? That means it won't be drawn to the screen. So there will be a new graph class instance. It will exist, but it will not be rendered onto your display. Okay? And the reason you do that is if you want to do a lot of things before you actually throw the graph up on the screen. You want to do a lot of stuff behind the scenes before you expose the completed graph to the viewer. Okay? So that's what this is about. This is creating a graph instance so that we can do stuff to this graph before we actually render it to the screen. So here we see this statement resizes it, and we can look at the graph method size. Let's see, where is size? There's size. Okay. And this tells us X start, X stop, Y start, Y stop. So those are clearly the minimum and maximum ranges of the X and Y axes. So if we look here, size, our graph that we got was ranges from 0 to 5 along the x-axis and minus 0.04 to plus 0.02 along the z-axis. Let's see if that's the case. Lo and behold, the x-axis goes from 0 to 5 and the y-axis from minus 0.04 to plus 0.02. Okay, fine. So we're understanding it. And now we see here it says save window view. And now we have a bunch of arguments. What does view do? So you get the idea. So you can decipher what the heck is going on. Here's the view argument of the view method. And it says M left, M bottom, M width, M height, W left, W top, and W width, yada, yada, yada. And we can see what these are. Okay. And we can tinker with this. With these arguments. Basically, I'll tell you right now, these last 4 arguments specify the X, Y coordinates of where the graph is shown, where it's rendered on the screen. And X starts at 0 on the left side of your display and increases to the right. And Y starts at 0 on the very top of your screen and increases as you go to the bottom. Okay? And each of these numbers then is a coordinate of a point. So that's the X, Y coordinate of the left. Is that the left upper corner or is it where is that now? 745.
It's top left, yeah.
So this would be top left. Oh, is Robert back? Or is that you, Kelvin?
I am back.
You're back. So you can see how you can analyze a session file and you can see how the expressions are added to the graph to say what things are going to be plotted, okay? And what these attributes are things like what is the color of the line, what's the line style, is it going to be thick, is it thin, is it dotted, is it dashed, okay? So that's it. And you can figure these out in your own time by referring again to the programmer's reference, read the fine documentation. Okay. And a lot of this stuff is very easily borrowable and repurposed, and you can redo it with Python to your heart's content if you want to do that.
And one little pitch while you're on that page, you notice how there's that lovely edit on GitHub link on the top of the documentation. If there's something that you think is unclear, you can literally just click on that link, and then if you're familiar with GitHub, there's the pencil icon. You click the pencil and create an edit, and then it can go in as a pull request, and we can make it public on the documentation. So please,
Okay.
if you think there are ways to make it cleaner, go ahead and make an edit, or you can also make an issue on the Neuron GitHub, and we will try to address it.
And again, the importance of what Robert just said is whatever you do when you're editing is not going to get back into the document that's displayed online. It will become a pull request when you're done and you submit it. It'll be a pull request, and somebody who knows what they're doing is going to review it and say, this looks like it's actually a decent edit and let's include it, or this isn't quite right, but it's an important thing to document correctly, so we'll take care of it. I'm glad you brought it to our attention. Okay, so this is truly a participatory project. One reason why Neuron is as good as it is and its documentation is as complete as it is because we get a little help from our friends. So if you know something and you'd like something to be fixed, or you can fix something yourself, go ahead and do it. Thank you very much. Okay, so I think at this point we've made a couple of important pitches, and I'm going to relinquish the stage to Robert, and I will stop sharing. There we go.
Well, hello, everybody. Thank you for your patience as we dealt with a fire alarm. Fortunately, turned out to be a false alarm. So again, thank you. Welcome. Today, you've been doing a lot of graphical stuff. We talked a little bit just now about some scripting and some insights and where the documentation is. I'm going to talk about some basics on the scripting, like the things that you absolutely need to know if you're going to do that. We'll have some exercises to do over the weekend. We'll talk about them on Tuesday. So there's a slight change to the schedule. I'm going to go ahead and throw out. So originally we were going to do just a whole bunch of scripting lecture didactic material today, and then a big demo session next week. Instead, I'm gonna talk for a bit. I'm gonna demo some things. We'll have exercises on that, and then next week we'll do the same thing. So just to give you a sense of how powerful scripting can be. So this is the entire code here for running the simulation. Wait, am I screen sharing? Yeah, I am.
Yes.
Okay, good. That's always nice. This is, sorry, still a little mixed up from the fire alarm. But so yeah, so here is the entire code that we need to run this particular model. This is, however, assuming that we have a session file, C91662.ses, but all it does is load a morphology. The reason that this is important, though, is that this is showing that we can mix and match whatever you do with the graphical interface. You can take it, and then it's just a single line in Neuron to actually load in the file. And we'll go through all of this. We'll make all of this make sense, but I just wanted to give you a sense of, we can load some libraries, we can load in a morphology, insert ion channels everywhere, give it a current clamp, set the delay and duration and the amplitude, initialize the simulation, run the simulation, and then plot it with a plot shape.
Just one question about that SES file. That's a SES file from that's a cell builder, right?
That is probably.
With its continuous create on, probably, because I don't know of any other tool that exports a SES file that contains a morphology.
I will. So this one literally came. This is the C91662.ses from Morse et al. 2010. It's a model DB entry 87284. We can share that on the we can share that link on the Slack in a little bit. But really, that's it.
Okay.
But yes, so you can have a morphology in a CSS file, as you mentioned, from a cell builder. And then in that case, this is everything that we need. And the nice thing about that is that means that you can play around with your morphology using graphical tools, make sure that all of it is correct. And we're going to go into this in some detail, not next week, but the week after. We're going to look at loading morphologies. We can get a lot of morphologies from neuromorpho.org. There's a whole world of things that you should know about defining shapes. Stay tuned. All right, so that's the pitch. So far in this course, like I said, we've been talking about all of the stuff that you can do with the GUI. Literally everything that can be done with the GUI can be done in programming. And so the advantages sometimes is that you can get more human readable scripts, but you can use the GUI to get insights as to how to write it, as we've already talked about today. So what is a script? So a script is just a file that has computer readable instructions for performing a task. And so in Neuron, we can use scripts for lots of reasons. We can use it to set up a model, to define and perform an experimental protocol, to record data, save and load data, do the analysis, all kinds of things. And writing scripts for Neuron, we can automate it, we can ensure consistency, reduces some manual effort. It makes it easy to swap things out, compare this, if you've written things in a consistent way, you can try it with this cell, you can try it with that cell, you can have an entire elaborate procedure that you can just swap out. You can do, automatically do a series of experiments. So how does this respond as conductances change or drug dosage or something like that? And if everything's set up, it allows you to recollect data. If you do make a change, you just have to, make your one little change and then go and rerun everything. And then it dumps to a database or wherever you saved it. And again, this gives a nice, complete, reproducible version of the experimental protocol. So everything is well-defined because there's programmatic specification. We'll talk about reproducibility at some point, maybe the week after morphologies. So it's certainly a very important feature in the scientific endeavor. We already sort of talked at this just a minute ago, but I'll point out at the top of the right of the Neuron homepage, there's this link for the programmer's reference. We saw it'll take you to a page on Read the Docs. You can go there, you can get all sorts of, well, it'll take you to the homepage, but then once you click into a thing, you can search there. It'll give you all kinds of references. So this is what the page for range var plot looks like. That's what the GUI calls the space plot. Yeah. And I think, so everybody, I think the way that we advised everybody to set this up was to use Python for controlling Neuron. Is that correct?
That's what we've been doing. We've been launching Python, either making Python read a script that then does from Neuron import whatever you want to import, or by in an instance where there isn't such a Python script immediately available, just starting Python and then manually doing from Neuron import h or h.com or h comma GUI.
All right, perfect. So in that case, so hopefully that means that everybody has a working Python setup on their machine. Just so that I can get a sense, can I get a thumbs up from people who feel comfortable with Python? All right, so I'm going to say it's about half of people. So that's good. So there's two main options for how to actually use Python if you're going to script it. What I personally do is I usually write my code in a programmer's text editor, like Visual Studio Code. So this is what VS Code looks like here. Nice thing is it's free. It's available for all platforms, Linux, Windows, Mac. It's got syntax highlighting plugins for all languages Neuron support. So that's Hope, Python, InModal. So if you have any of your InModal keywords, to highlight them and all of the colorful programming ways that these things do. And then if you do that, you save it to a file, then you can just you can run that file by Python and then the name of the file, and then it's going to run it. And here, this is a script, and we'll work our way through creating one of these later today. But what this is doing is this is defining inserting Hodgkin-Huxley channels into the SOMA and looking at an action potential. So here's the full code, and here's how we run it. We just type Python and then the name of the file. You do this from a terminal. I think by now everybody's figured out how to launch a terminal. The other major way to do this is to use what's known as a notebook. So especially Jupyter notebooks. So this is one that's running locally. There's also cloud providers. So Google has what's known as Google Colab, colab.research.google.com. It's a free cloud provider for Jupyter notebooks, basically, and everything's stored in your Google account. And then the only thing that you have to remember is explicitly to install Neuron at the beginning of your notebook. So that's !pip install Neuron. The nice thing about notebooks is that they allow you to mix code and the figures, and you see what goes with what. It's all very clear and together. And so if you're using a notebook, you'll get your plot shape right in the notebook, and then you can rotate it around and interact with it in that environment, and then and so forth. So that's sort of my intro. Does anybody have any questions before I actually? So what I'm going to do is I'm going to move in. I'm going to talk a little bit about Python, and then I'm going to just to make sure that we have a common understanding of some of the basic syntax, and then we'll get into Neuron and Python. Does anybody have any questions before I get into that? And if you do, please unmute, because that's probably the easiest. Okay, hearing none. I just want to give, so apologies to all those who already are familiar with Python, but I'm just going to give a little bit of a background to make sure that we're all happy. One of the most important things that you can have a computer do is to tell you a result. Because if you can't actually get the results of your calculation or simulation, that's a problem. So in Python, Python provides what's known as the print function. And so it's print, P-R-I-N-T, takes parentheses, that's the general syntax for calling a function. And then you pass in whatever you want it to print out. If you put quotations around it, could be single quotes, could be double quotes, could actually be triple single quotes or triple double quotes. But in any case, then it's treated as an exact phrase. Otherwise, so here I print the exact phrase. Neuron is a great tool for simulation. Boom, there it is. If alternatively I asked it to do a calculation, print 5 times 3 plus 2. By the way, if you haven't seen this, asterisk is often used for multiplication. So this will print out 25. You could imagine that somewhere else I've defined a thing called the soma of my cell, and I want to see the soma's diameter. So one of the common motifs in a lot of programming languages, and Python is no exception, is that if you want to see a property of a thing, you take the thing, in this case soma, you do a dot, and then the property. So this is going to tell us the diameter, diam for diameter, of the soma, which in our case is 10 microns. And we'll see how we can set it, but well, it's going to be soma.diam equals something. We'll get there though. Does this make sense though to everybody? Okay. All right. So of course, doing a calculation is no good if we have to do it every single time. One of the great things that computers let us do is give things names. It's one of the most powerful techniques in computer science and mathematics. Just giving things a name. So if you store something in a variable, so if you want to store like the diameter, let's call it diameter, we'll say diameter equals 4, then any place that the word diameter appears outside of an, not in a string, it's going to print out exactly as is. So the diameter is 4, comma is just sort of joining. It's going to print the first thing and then the second thing. The square of the diameter is diameter. Double asterisk means raising to a power. So this is diameter to the second power, 16. We might want the diameter squared if we were trying to calculate the surface area of a thing, for example. Or, the other important thing, especially in programming neurons, is being able to do the same thing to multiple pieces. And so the way that we do the same thing to more than one piece is we can store all of our things in something that we can loop over, like a list. So here we're creating a list of items. So a cell parts list maybe has 4 items. Our cell has a soma, by which here I just mean literally the exact letters SOMA, but a soma, an apical, a basal, and an axon. And then I use the square brackets to indicate a list. Lists are things that are stored positionally. So there's a 0th item, a 1th item, a 2th item, and a 3rd item. And so I can loop over my list, right? So for part in cell parts, so for statement means I'm looping over something. So I'm going to do it everything that's inside my for loop, which I indicate with a colon to indicate the beginning, and then indentation indicates everything that's within that set. So everything that's indented underneath this colon is going to happen exactly once for each item in my cell parts. So it's going to loop through this. It's going to, for the first time, the variable part is going to be equal to soma. The next time it's going to be equal to apical. The next time it's going to be equal to basal. The next time it's going to be equal to axon. And then it's going to stop and it's going to go on to anything else that I've written in my script. So you could imagine that I could do this to set properties across a whole bunch of cells, a whole bunch of cells in a network, or property parts within a cell. So maybe the apical dendrites have many pieces, many are composed of many sections. We can loop over them and assign, we could assign ion channels or parameters to those things. And we can do that with a for loop. We could also grab a specific item. So this is the item in the 2 position. In most, but not all programming languages, you start counting at 0. So the 0th position is soma, the 1th position, and this, by the way, is why I'm calling it 1th instead of 1st, to indicate that it's, here's the 0th, here's the 1th, it's the thing after, here's the tooth. So basal is the item in the 2nd position, in position 2. So it's going to print out the literal BASAL. And we can check to see if an individual thing is within our cell parts. So is the literal letters brain one of our cell parts? No, it's not. It says false. But if I put in soma or apical here instead of brain, it would say true, the capital T in Python. Does that make sense? Loops and lists are extremely powerful tools for programming. So we're going to use them a lot. All right, a lot of times though, there is no inherent order, right? Lists are fundamentally ordered. There's things that come in different orders. We could instead just give our own identifiers. So I could have what's known as a dictionary. If you've learned other programming languages, this is sometimes called a hash array. But wherein I use keys. So the soma is the key, it's going to have a value of 10. The axon's a key, it's going to have a value of 2. And just like when there's a numbered position, I'm going to use square brackets to grab an item by its key. So this is going to look up in my diameters dictionary the value that's associated with apical. Well, here's the apical key has an associated value of 5. So it prints out the value of 5. And we do this basically anytime where there's no natural order, right? We'll just use, so I can't grab the item in position 0 because there is no position 0, but it does make sense to talk about apical, right? Cells have parts, they don't necessarily have a natural 0th item of a cell. If we do want to loop over these, we can grab all the key value pairs by looping over dot items and then just giving different variable names for the keys and the values. So when this loops over, it's going to, for each item within diameters, and there's 3 items. There's an item that has a key of soma and a value of 10. There's an item that has a key of axon and a value of 2. There's an item that has the key of apical and the value of 5. For each of those, so it's going to assign the key to name and the value to diameter, and then it's just going to run this code every single time. So the first time through, it's going to print the diameter of soma is 10, the diameter of axon is 2, the diameter of apical is 5. So does that make sense? Okay, nobody says anything. I have no idea what's going on, but all right, I got a thumbs up. Excellent. I'll take it. All right, fundamentally, the other big thing in programming is what's known as the do not repeat yourself principle. And one of the ways that we can avoid repeating ourselves is if we're going to use a calculation more than once, we'll give it a name. Again, name's very powerful. We can do this using the def keyword. We'll define a function. So I can define a function that's going to calculate the volume of a cylinder. It'll take some parameters, a diameter, a length, and then it'll do a calculation. And when I've done however much calculation I want, you'll see that this is indented because this all is part of that definition. Once I've done whatever calculation I want, I'll end by returning my result. So the volume of a cylinder of a given diameter and length is pi over 4, the diameter squared times the length. Right, and then so I could calculate the volume of a specific cylinder if I know the diameter is a number and the length is a number. But for us, you could imagine, well, maybe I have a section, and the section, the apical section, let's say, has a given diameter, and the apical section has a given length. And we indicate in Neuron the length of a section by a capital L. And again, we'll get into, I'll explain all of the Neuron stuff more specifically, but in a bit. All right, so if we're doing a calculation more than once, we give it a friendly name so we can just refer to the name instead of the individual pieces. In Python, we have a lot of Neuron, we have a lot of modules. There's really sort of modules for everything in Python. They're just libraries. So there's a whole library of mathematical routines. So like the cosine, right? So if I'm importing math, that's going to give me everything that's within the math library. And then I can do math.cos to get the cosine functions, math.pi to get the value of pi, math.sine to get the value of sine, the function sine, and so forth. And so the cosine of pi over 3 is, of course, 1/2. We can also load specific items from a module and give it a shorthand name for the module. So you've already seen, for example, from Neuron import h, GUI, loading, if it was just from Neuron import GUI, it'll load that graphical interface. H is this programmatic thing. We're going to use it mostly. It's going to be a primary world. It's going to be a primary portal into the Neuron world. So h.rangeOverPlot in some of those examples, h.section if we want to create a section. We'll see all of this in more detail. We can also give things shorthand names. So the pandas library, I could just call PD. And there's tons and tons of useful Python modules. And you have these slides already. They're posted on the general channel, and we'll move them over into the FTP site as well. Here's some talks. So there's a whole, Python provides a huge, so math gives you math functions, so does NumPy. Pandas gives you a lot of data science and database access. If we have time next week, I may give you some examples of pandas. sklearn is sort of your go-to for machine learning that doesn't involve any NLP. And there's a ton of graphics libraries for Python, most of which play reasonably, many of which play well with Neuron. So that's things like Plotly and Plot9 and Matplotlib. And of course, you can always use the regular Neuron graphics as well. So these libraries, many of these libraries are included with Python. If you download like the Anaconda install, a lot of libraries are going to be included in that. If you're just using whatever came with your like Mac or Linux, you may not have everything. But the way that you install something is by name. So you'd say pip install and then the name of the library. So if, just like you probably did for installing Neuron if you were using Linux or Mac. One of these graphics libraries is called Plotly. I'm going to actually skip this, but here's examples of plotting a linear function, the identity function, and the square function, and then making a pretty picture. And the reason that I like, a lot of people use Matplotlib. The reason that I like Plotly is because it gives you really interactive graphs. Matplotlib kind of does, but Plotly is more interactive, especially inside of a Jupyter notebook. But here's examples. You can use whatever you want with Neuron. The one other sort of thing that I want to highlight, we're often going to run simulations for a while here. So let's say I want to run a simulation for, I'll set a variable t-stop to indicate my end of my runtime. If I want to actually throw that number inside of a string, the way that I throw a number or a value or a calculation that I might do inside of a string is to put the letter F out in front. It becomes an F string then, or it's analogous to what JavaScript calls a template string, if you know about that. But so here, an F string, we should stop at t equals, and then whenever it sees the curly brackets and then an expression, it'll just look that up. So here it's curly brackets t-stop, it'll look up t-stop, and it'll throw the value of t-stop in here. So it doesn't print out, my string doesn't have any curly brackets, it's just the string, we should stop at t equals 10 milliseconds. And there are all kinds of crazy things that you can do with this, and you can look this up, but you want to round stuff, you can round it, and here's a syntax for rounding. You can do all kinds of things. If you want to get help on an individual thing, there's two main ways of getting help within Python directly. So if from Neuron import H, I now have a thing called H in my Python interface. And so I could print out the directory dir of H. And this is just going to list literally everything that's available within H. So that means that since I see there's an AP count, that means that I could do h.ap count, or h.alpha synapse, or h.atol tool, or h.exp2sen, or h.exp. Sorry? Okay. I can also get help on a specific thing. So I can say help of h.iclamp, which you may or may not know is a current clamp. And then it'll print out a whole bunch of documentation about the current clamp, and it's basically whatever existed on the read the docs page at the time your version of Neuron was generated. And there's a ton and a ton and a ton. So if that doesn't help you, doesn't give you what you need, there's a ton of documentation available in general about Python and how to use Python. The official documentation is great. It's docs.python.org. Stack Overflow, if you haven't discovered Stack Overflow yet, it's amazing. If you Google a question about programming, it's almost certainly going to be one of the top hits. We've already seen the Neuron Programmers reference, and I think you've also seen the Neuron Forum as well. So this is just a very, very breezy overview of basic syntax. If you'd like a more structured introduction, I know this was extremely fast. If you'd like a more structured introduction, so I co-taught a informatics series last summer, ycmi.github.io/summercourse2020. Again, this link is in the slides, which you already have. And in particular, on day one, the first day, it's an introduction to Python for data science. So all of this is sort of presented in a health context, but it's a much more structured. You see there's 2 hours of material here, plus exercises and solutions. You can work through all of this. You can learn any parts that you want. So that's my suggestion if you want a more structured introduction. All right. But does anybody have any questions? I know it was a bit of a whirlwind, but does anybody have any questions about what we talked about basic Python before we get into Neuron itself? Okay, hearing none. Let's talk about doing stuff with Neuron. All right, so first of all, we've already said you're almost always going to need the core neuron functionality that's available within the H submodule. So what we always start, basically every neuron code that we're going to write, basically ever, is going to start with from neuron import H. Cool. Saved you one line on all of your publications now. It's often convenient to write code that embodies units. You're probably going to end up using Neuron's default units anyways, because they make the most sense in a neuroscience context, but occasionally you might find rate constants that are expressed, especially if you're doing anything like chemical, you might find rate constants that are expressed in, like, I don't know, nanomoles per second or something, nanomolar per second or something like that. And so if you do, that's a great reason to just grab the units from neuron.units. If there's chemical dynamics that are going on, there's an RxD submodule. We've already seen the GUI submodule. There's a handful of other things for various purposes, but we'll get to those as they come up. Okay, second line that you're almost always going to need. You're probably going to want the standard run control library. And so Neuron itself built in provides basically the ability to initialize the simulation and the ability to go from one time to the next time. And you may or may not have seen that the next time, well, when's the next time? Well, it depends. What's your time step? Are you using fixed step or variable? There's tons of options on that. We'll get to that when we talk about numerical methods. But what's the standard run control library is going to do is it's going to give us some high level functionality that allows us to say, I want to run until a specific time. And then maybe I want to make a plot, and then maybe I want to run a little longer and see what happens. So I want to save my state and go back to that. And we'll see about saving state and going back to that next week, probably. But before we do this, we have to actually have a place for anything to happen. So you'll know that you remember that our basic unit within Neuron is called the section. And so if I'm going to create a section from the command line, I'll say h.section, and then I'll give it a name. So h.section name of apical is going to create a section. It's going to print out, show up in all of our graphical tools, all of that jazz, using the name apical. But I also need to hold on to this, right? I need to be able to access it. I need to be able to manipulate it. So I'm going to assign it to a variable as well, right? So I'm going to say apical equals h.section with the name of apical. The variable name and the name that prints out don't have to match, but you'll be much happier if they do. So the reason you might think, well, why would I ever want them not to match? Well, what if I'm looping over something? What if I'm looping over all the sections? I'm going to have the original variable, which is the apical. But if I'm looping over all the sections, I'll have a loop variable called, let's call it sec, let's say. And at some point, that sec is going to be equal to the apical, and maybe somewhere else it's going to be equal to the soma, and some other time it's going to be equal to a basal dendrite, right? So it's perfectly okay to have many variables that refer to the same section object, right? Okay. But if I do, so I can, have another variable that refers to this guy, a equals apical. Okay, well then now I could refer to it by apical or by a. I could check to see if two things are the same in Python. Well, okay, that's a slight lie. I could check to see if two things are equal in Python using the double equal signs. So this is going to print out true if they're referring to the same section in this case, or false if they're not. If I want to get that string name, I just use str. So the string of the object is going to give me the string representation. So S here is the string, the literal string apical. If there was a cell that was associated with this, then the section name that's going to come out as the string will include the cell's identifier as well. So if there is a cell that's associated with this, I can identify it at the time of creation by just passing in cell equals. And so this is typically going to happen inside of an object. So cell equals self, or cell equals whatever object you want to associate with it. Right, and you've seen sections, they mean exactly the same thing from the programming side as they do from the graphical interface. So a section is a length of unbranched cable. It's going to have a length. It has a diameter. The diameter could be varying, but let's just suppose for the moment that the diameter wasn't varying. So diam. If it does vary, if I ask for the diameter, anybody know what happens if the diameter is varying along the length of a section, and I ask for the section's diameter? Anybody know what it's going to give me? Well, give me the one in the middle.
Okay.
So if I want to create a, if I want to discretize this, I want to break it into segments. I'll just set the inseg property. So soma.inseg equals 3 would break my section into 3 parts. Soma.inseg equals 5 would break my section into 5 parts. You'll notice that I'm emphasizing odd numbers. Anybody remember why we like odd numbers for inseg?
So that there is no ambiguity regarding the midpoint of the section.
Exactly. If there's an even one, we see that the midpoint doesn't actually belong really to either. It's exactly at the boundary. But if I multiply something by an odd number, if I want to do, again, we'll talk about numerical details later on in this course, but if I multiply by an odd number, all of the old nodes are preserved. So I can talk about questions like convergence and things like that.
Well,
Ted,
if nseg is even, the midpoint does belong to something. It belongs to one segment or another, but the decision as to which one it belongs to is up to a round-off method used by the particular math library that you happen to be running at the moment with the particular version of Python that you're using. And you don't want that kind of ambiguity. You don't want default interpretation of a round-off error to affect something that you're going to be doing many, many times, which is referring to the midpoint of a section. So that's why you choose an odd number. You will get an answer if you've got an even number, but it'll belong to a section that's either below or above the point that you intend.
Absolutely. But I mean, again, also the convergence issue is often important as well, multiplying by an odd number. Yeah, there's always some value, but it may not be what you want it to be. And reproducibility, again, we have a whole talk, a whole talk that's devoted to reproducibility discussions. And we really want to make sure that our simulations are consistent. We want them to be consistent if we're running in parallel. We want them to be consistent if I take my code and I give it to you, we want you to get the same results. So, all right, so what do you want to do? So now that you have a section, then what might you want to do with it? So we can loop over a section. If we loop over a section, so if I create a section, I'll say dend is h.section, I'll give it a name. It's got a length. By default, this is in microns, but again, I encourage you to include the units. So the length of 3 microns, a diameter of 2 microns, and an inseg of 3. And then I can loop over my section, and a section is a bunch of segments. So naturally, if I loop over a section, I'm going to get each segment. So if I print out the segment and the segment's area, I'll see, oh, look, well, the first segment is dend of 1/6, and its value is 2 pi. The second segment is a dend of 1/2 and its value is 2 pi. Third segment is a dend of 5/6 and its value is 2 pi. Its area, sorry, not value. Its area is 2 pi. And the default location that it's showing us is the center of the segment. So if I have if nseg is 3, then that means that the first segment is running from position 0 to position 1/3, and so therefore its center is 1/6. And so that's where these x coordinates come from. If I want to know the x coordinate, if I have a given segment, I can just do segment.x. Again, remember, it's a standard programming convention that if you want to know a property of a thing, you just ask for the thing dot the property that you want to look up. So seg.x is going to give me the x location that's associated with the segment. The segments also have a section that's associated with it. So it's seg.sec is going to give me the section object, and I can see if it's the dendrite or not. In this case, it is, because the segment was defined as the segment that contains the center of the dendrite. And to be abundantly clear, this is always a true state. So if I have seg is dend of 0.5 and I change nseg, it doesn't matter, because my segment will still refer to whatever segment contains the center of the dendrite. Right? It's not going to break. It's not going to mean anything. What it is always whatever section and whatever location. So we'll always refer to the right thing if you change your discretization. But you probably don't want to do it, but it will do the right thing. As you're looping over things, you can, set properties on any individual segment. So segments don't have to have all the same values, right? So maybe one segment has a higher sodium conductance. So in this case, one segment has a bigger diameter. And so if I set that segment, so the segment containing the center of the dendrite, right? So den parentheses 0.5 is the segment containing the 0.5 location on the dendrite. Yeah, sorry, there's a question.
Oh, I just wanted to ask, can you change the name of the section once you define it? After defining? Like
This name?
Yeah.
This name, no.
Okay, so we have to create another section with a new name. That's how we can do that.
You can create it, yeah, but you can always do that.
Okay.
You can change the variable name, but that doesn't change how it's going to print out.
So, but what is this use of this name? What does this name suggest?
So this name, so when I give it the name dend, when I print it out, it's going to print out the DEND. Okay. So because otherwise, if I'm looping over a whole bunch of stuff, I'm going to get it's going to make up a name if I don't give it a name. And if it makes up a name, it's not going to be anything meaningful to me.
Is it the name we change in GUI, the cell builder? We click and the change name and thing. That's the thing. That's the same, like in Soma and AP, things like that we use to write. And
I doubt very much that would let you change the name here. I don't think that's going to work.
Okay.
So I think you'd want to just create it with the right name.
Yeah, what you could do with the GUI is, if you did have a model cell that exists, you can import the morphology of that cell into a cell builder, but you're not actually wrapping the existing cell inside a cell builder. You're making a copy, and then you can do anything you want with that copy, but the cell builder is not going to be able to do anything about the model you created with Python.
I see, okay.
So you can't touch it with the cell builder or any of the GUI's tool. You're not going to be able to change that name.
Right, makes sense.
Okay.
Yes, yeah.
But one of the nice things is, since you're writing this in a script, like literally, if you just change your script and rerun it.
Right. Yeah, that's good. No problem.
But this name, so anytime that the name gets printed out, anytime that you see a printout that actually refers to it by name, that's where the name variable goes. So like this shows up in your plot what tool, you'll see the name that you define here as well.
Yeah, sure. Thanks.
So,
And the
so
other,
in your
Yeah, go ahead.
getting X in section example, if you change the print statement, the second argument you change to seg, you just got rid of seg of the equals dend. You would say print seg X, comma seg sec. What you would have got would have been 0.5 and then dend, right?
well, let's find out. So can you guys see my terminal here?
That's good.
None import H. And I will say dend is going to be H.section, and I'll give it a name of dend. And then I will say seg is equal to dend of 0.5. So let's print seg.x, 0.5, not surprising. And let's print seg.sec, and it's dend. So what happens if I didn't give it a name? And now if I want to print out, well, I'll just print out the section directly. It's a name. You know.
I'm okay
except-
with that. I'll use that. But it'll be
The-
different every time I run the program.
Absolutely. And so by giving it an actual name deliberately, we ensure reproducibility.
I wouldn't even be able to execute my code if I wanted to print a graph that showed the membrane potential at the middle of this section. During this session, it would be double underscore neuron sec underscore and then all that garbage. But the next time I run neuron, it might be a bunch of different garbage.
Yep.
So my graphical use, my graphs wouldn't be able to access the variable correctly.
Yeah, it would absolutely break that.
Okay.
But it's a perfectly valid section name. So from H dot. So you could use H dot underbar neuron sec. But again, it will not be the same from one time to another.
It's a good way to write obfuscated code.
That only one runs the first time.
Yes. Destroy this program after you run it.
There you go. All right. So, and just, I want to point this out. So I've talked a lot about cylinders. We're going to get to morphologies in a great deal of detail, not next week, but the week after. But I do want to emphasize that none of this is limited to cylinders. It's just convenient to start out thinking about cylinders. All right. So I have a section. Well, presumably I have more than one section in my cell. If I want to connect them together, I use the connect method. And so what the connect method does is it's going to take den2 and it's going to stick it at a specific location that I specify. So den2, the beginning of den2, the 0 location of den2 is going to be stuck somewhere. Where is it going to be stuck? It's going to be stuck on the 1 location of dend1. So in my topology, I've got dend1 runs from 0 to 1, and then at the 1 on dend1, that's where I'm going to stick dend2. And you could imagine that I'd also maybe want to stick a third dendrite. You know, I could have many dendrites coming out of the same point if I were so inclined. Yeah. There's a question on Slack. I'm going to punt for now on that one, but we can answer it offline and we'll get to it in 2 weeks. But yeah, so if I want to look at, if I want to create a whole bunch of sections, I can attach them together using connect, and then I can view the topology using topology. So h.topology. So let's look at what this does. So here's an example, right? So if I have, and in practice, you wouldn't actually do this in brute force like this. You'd use for loops or you'd use data formats. So we'd load in an SWC file or something like that. But let's just imagine that instead we're doing this brute force. We're creating a whole bunch of sections. Soma is h.section, proximal apical, and so forth. And then I connect them in a certain way. So the proximal apical dot connect is going to go onto the Soma. If I don't specify a location, the beginning of whatever I say here goes at the end of whatever I say here, which makes sense, right? I'm going to connect something to the end usually. The main exception is actually in this case of like a pyramidal cell where I'm going to want my apicals to be on the opposite side of my basals. So if I stick the apicals to connect at the one location on the soma, then I probably want my basals to connect to the 0 location on the soma, and I can do it that way. And then I can just connect things onto them. So this is like, well, this is literally doing what the cell builder does. You start with the soma, and then you draw something off of it, and it's connected. And then you draw something off of that, and it's connected. And in fact, if you're using continuous create, you'll create this structure for you automatically. And then even if you use the graphical tools to create this, you can use h.topology, and it'll print out this structured representation. And so what I see here is that I have the soma, and at the end of the soma, where the soma ends, is where the proximal apical begins. Where the proximal apical ends is where apic 1 begins. Apic 2 is not further indented, so it begins at the same point. The proximal basal, on the other hand, you'll notice is not as far out on the soma. It comes at the 0 end of the soma. But the distal basal, are going to be attached to the end of the proximal basal. So does this example make sense? And you can always pull up a shape plot. If you're using interviews, it's not going to tell you which section is which. If you're using Plotly or Matplotlib, you can mouse over it and see which section is which pretty easily. And we'll get there. But conceptually, does this make sense? We define sections, we stick them together using connect. All right. We've already said we can specify the length, we can specify the diameter. If I do want to specify coordinates in 3D space, I can use point 3D add, and that's going to give me an X, a Y, a Z, and a diameter. But again, usually you're not going to want to do this by hand. Usually you're going to want to load in morphology that was traced with NeuroLucidor or something like that. All right, you already know this, but I'm going to say it again anyways. Hodgkin and Huxley worked with squid. Neuron's default units are built around the squid. So if I just create a section and I do nothing, the diameter is going to be 500 microns. This is not appropriate for mammals. It's perfectly fine for the squid giant axon, but don't use a 500 micron diameter for mammals. If you're studying mammals, you're going to want something smaller. The axial resistivity is 35.4 ohm centimeters in squid. If you're studying mammals, you're going to want to specify something different. Let's say about 100 ohm centimeter. Perfectly reasonable, perfectly happy temperature for squid is 6.3 degrees Celsius water. This is Neuron's default temperature. If you're studying mammals, that's not a happy temperature. You're going to want to set something different. Also, to be abundantly clear, if you're studying mammals, you shouldn't be using Hodgkin-Huxley channels because they're not for mammals. All right. We'll get to this a little bit more later when we do an example, but a pro tip here, though, once you set up your thing, or as you're setting it up, it's often convenient to put everything inside of a class. If you know about programming, if you know object-oriented programming, it adds a couple of extra lines. So I'll say the class of pyramidal cells, and then I have to add this define double underbar init self. And what this says is that every time that I want to create a pyramidal cell, I'm going to do the same rule. And so that means that this pyramidal cell's, the self of that pyramidal cell, has a soma, and it's going to be equal to whatever. So it's going to be a section that has a given name and belongs to this cell. That soma is going to have a length. In this case, also happens to be equal to this diameter, which also happens to be 10 microns. And the reason that I would want to do this, it's 2 extra lines of code and a few extra self dots. But the reason that I want to do this is because, yeah, maybe I'm starting out simulating one model. I'm trying to understand one cell. But one of the things that's super powerful about this thing is I've defined a template. It's a It's literally, this is what pyramidal cells are like in my model, in my understanding. And then I can have one of them, so I can say PYR1 is pyramidal, open close parentheses, right? I can have one of them, and then I can access that particular cell's soma's diameter. Again, dot gives me different properties, right? So PYR1 dot soma is going to refer to the soma of the PYR1 cell. And then again, dot diameter is going to refer to the diameter of that. So I could do that, and it has a nice sort of hierarchical thing and allows me to keep track of things. But importantly, once I've done one, once I've studied that one, once I'm happy with that one, if I put this in a class, I can make many of them. And so I figure out, I get the cell working the way I want it to. And then now all of a sudden I want to talk about a network of these things. Well, I'm going to need many of them. And if I have put it in the class and I've written those 2 extra lines, remember, it's just 2 extra lines of code, then I can create a second one. And that one has independent variables and I could change them. Or Python has what's known as a list comprehension. If you don't know about this, don't worry about it. But the point is, in Python here, this is a single line that creates an array, a list of 1,000 independent pyramidal cells, right? So those could all, you could imagine, get synaptic inputs going into them. They could be connected in any sort of way. So once I've defined my cell, if I took those 2 extra lines and a few extra self dots in there, I can just create a gazillion of them, and then I can study it. And so since there's always a possibility that maybe I'm going to want to have a network someday, I think it's my advice to you is to go ahead and do those 2 extra lines, because it may come in handy at some point. We'll look at this in a bit, but so programmatically, you've already seen so graphically, you've already seen the shape plot. Everything that we've done, actually, let's just do this, because let's just start a new one. So from Neuron, nope, that's Python. So I haven't launched Python. So Python, from Neuron, import H and GUI. So if I'm going to create a section, so let's just say main is h.section with the name of main. Den1 is h.section with the name of den1. Den2 is h.section with the name of den2. And maybe these things have diameters, so let's say 10 let's just say 10 microns, and den1 has a diameter, and it's going to be the same as den2's diameter, which is going to be 2 microns. And then now I'm going to say that these 2 sections are each connected to the end of the main. So den1 is connected to the main, den2 is connected to the main. So I've now defined a shape, at least conceptually, right? So I have a main section that's got 2 things coming off of it. Well, what does it look like? Well, I can do this in a couple of different ways. I can do a graph shape plot. And there it is. I see my my cell. It looks kind of like a Y shape. Now you may think to yourself, I didn't say anything about angles. How did it know what angles to put it in there? Well, and here's the punchline. If you don't tell Neuron any angles and you ask Neuron to give you a pretty picture, it has to pick some. And so it will, and often makes a reasonable choice. But again, if you do have these 3D points, if you do load morphologies, then all of that information is there. But since we didn't tell it that, it had to make a guess. We don't see the diameter here, but remember, you can always right-click on this, shape style, show diameter. And then there we go. We see that our main section has 5 times the diameter of our children's sections. We can also embed all of this inside of a class. We can use plot shape with an argument of false to have it plot using Plotly or Matplotlib. And then we can make a pretty picture that way as well. And then those are interactive using traditional Python graphics instead of interviews if you so desire. And just to point this out, if you have a given plot shape, you can always save it to a file using the plot shape.print file, and then just give it a file name, and it'll save it there. It saves it as an encapsulated PostScript file. But so the point here is anything that you define here, you can view in the graphical tools. You can mix and match what you're doing in the code and what you're doing in the GUI tools. We can set variables. So if I can set the voltage, well, the voltage is a property of a thing, right? So if I have a cell, my cell, and it has a section called main, and that main has a voltage, well, I'm going to use the dot notation, right? Every time I want to access a property of a thing, I can do dot whatever. So with my cell's main section's V, I can set the voltage to be 50. I can set the voltage to be 0. I can set the voltage to be negative 65. I can use plot shape either graphically, or this is the commands. If I wanted to do it using plotly, if I wanted to do this with interviews, it's exactly the same thing, except I drop this last line and I just don't say false. And then that would give me a color-coded heat map of what the cell looks like, the membrane potential across space. And I think this will all make sense when we actually do some examples. But any big questions on that so far? Okay, we can also do a range var plot. So range var plot says I want to know the path, or space plot is what it's called from the graphical tool. So if I want to know what something looks like as I go from the 0th position on the main cell, on the main section, to the 1th position, to the 1 position on DIN 2, I can create a range var plot. RVP is h.range var plot of whatever my variable is that I want to plot, where I start, where I stop, and then I can just say rvp.plot. If I want to plot on Plotly, I can do rvp.plot on Plotly and show it. Again, similar for interviews, matplotlib, plot9, bokeh, whatever your favorite graphics library is, it probably just works, hopefully. We'll do an example of that. We can look at the voltage, sodium. So we've seen before, I think, sodium inside the membrane is NaI, sodium concentration outside the membrane is NaO, sodium current is INA, sodium reversal potential is ENA. Obviously, the same thing is true for potassium, except you replace the Na with the K, or for chloride, except you replace the Na with the Cl, and so forth. Remember that Neuron is only going to define values for these things. It's only going to keep track of these things if you have a mechanism, like a mod file, that you want that uses the ion. Otherwise, it doesn't make sense to keep track of chloride concentration if you don't use that ion in any of your calculations. So you can get lots and lots of different variables that you can plot and color code your plot shape with. You can record them using what's known as a pointer. So the convention in Neuron is that if I have a property, so seg.v is going to be a specific segment's voltage, or if I want a pointer, which is basically the concept of voltage, the voltage at that location, but that voltage is going to change over time. So just I want to refer to the voltage at a specific location, I'll say the segments dot underbar ref underbar v, and so I'll just stick an underbar ref underbar anywhere, anytime that I need to do anytime that I need to record something, anytime that I need to feed some complicated waveform into Neuron, I'll use pointers, and then I'll just associate the concept of a particular location's variable. We'll see more of this in a bit. Hopefully that'll make more sense then as well. If I have a distributed mechanism, so something that I got from a mod file that's not a point process, so like Hodgkin-Huxley, right? So Hodgkin-Huxley, you'll remember is HH in the Hodgkin-Huxley is HH in the graphical tools. So that means for us, we'll talk about it as H.HH, right? So if I want to insert Hodgkin-Huxley into the apical section, I can say H.HH.insert into the apical section. Or if I want to insert it into a whole bunch of sections, I'll just H.HH.insert it into a list of sections. You could imagine that I can use this to insert it everywhere. And in Neuron, H.allsec is the convention for everywhere. So this is going to insert Hodgkin-Huxley channels everywhere. You may also see as an alternate syntax, a section.insert a mechanism. That's fine too. And in older code, you'll even see this mechanism expressed as the string HH instead of H.HH. That's also fine. But if you do it this way, you can only insert into one section at a time, versus if you use the mechanism first, you can insert into your entire model in one line. And I think you guys have already seen mod files. Is that correct?
True.
All right. So then I'm going to not spend a lot of time on this, but again, so the fundamental point is that I'm going to create, if I create a section, that's just the cable theory itself, right? So this is the cable theory equation. But if I insert kinetics into that section, so that's whatever's defined as the mod file. So all of these nasty equations from the Hodgkin-Huxley is just expressed in Neuron. We've given it this name, right, of H.HH. So
Those
I
are
can
nice
insert,
equations. They're not nasty. There's nothing nasty about them at all.
And so in Neuron, we don't actually provide a lot of ion channel mechanisms built in, but there are hundreds that are literally hundreds that are available on ModelDB. So we'll talk about ModelDB some more when we go into when we talk about reproducibility. And you can always compile these with enter an IV model. We've already talked about mod files. I just want to give a shout out for, if you look at the Hodgkin-Huxley ones, you'll see that they embed ontology information. So if you do find mod files that use these represents keywords, that can help you figure out what the what the mechanism is representing. All right, so here this is Kebi is on chemical ontology, and so this is a code, standard code you can look up that refers to the sodium concept, right? So we can always interpret. This gives us semantic meaning, semantic interpretations to our mod files.
One thing I should mention is I've seen people already start to take advantage of files that have had such ontological edits added to them, and then they modify the code, but don't modify the ontological markup. And so I think we should mention that if you do indeed, it's perfectly fine to take working code that contains these represents statements and use that as a starting point for your own modifications. But if you do modify things, probably safest to comment out the represents so that they so we don't mistake these for don't start getting them confused with other things.
That's a fair point. I would say I would actually go further. I think it's generally a bad idea to comment actual code. Like commenting code is including code in your comments is extremely important. Please do that. Commenting out code is extremely confusing and risks getting yourself into trouble. I think you're better just removing it entirely. But that's me. So I would delete it if it's not referring to, in this case, a sodium channel or potassium channel. You can always look these things up. BioPortal is where to go to look that up. And you'll find identifiers for everything that you could imagine and more. If I want to specify, so that's for a distributed mechanism. So for mechanisms that are expressed in at a specific point, we use a different syntax. So if I have a current clamp, which is an I clamp, H.I clamp, I can say that's going to live at a specific point. So I'm going to have a current clamp that exists at the center of a soma. So I'll pick my point process mechanism, H.I clamp. In the graphical tool, you would have just seen I clamp, right? So H.I clamp is going to exist at the center of the soma. And then I'm going to create that, and I'm going to assign it to a variable. And by the way, I keep stressing assigning to a variable, and fundamentally, the reason for this is if there's no variable that refers to a thing, then the thing doesn't, then the thing might as well not exist because I have no way of getting back to it, right? And so literally in Python, if there's no variable that refers to a thing, Python just makes it go away. Right, so if you want that I clamp to continue to exist, to continue to have an effect, you have to make sure that there's a variable somewhere that gives you a path to getting there. But if I have a specific point process, in our case PP, I can always query it. I can always go back and figure out what it was, so where it was. So if I have PP, I can say, well, get segment. And then that's going to return the segment. And then we've already seen I can, once I have the segment, I can do .sec to get the section or the normalized position using that .x. I can get all kinds of other queries that I can do on this. And this is, by the way, a fundamental principle of Neuron. Anything that you can construct, you can, I hope, figure out what it is. You can always introspect. You can always figure out what you need to know to actually make it. So Neuron provides the tools for not just describing the model, but once you have the model set up, you can then go back, query it, which is fundamental to being able to analyze it. It's fundamental to being able to reproduce it. If I have a parameter that's associated with a specific mechanism, well, again, dot notation, right? So if I have a specific value of GK bar that I want to read, well, let's say it's on the apical, the segment containing the 0.2's location has Hodgkin-Huxley, let's assume. So then it would be .hh to give me the Hodgkin-Huxley mechanism at that location, and then .gk bar to give me the variable GK bar that's associated with the Hodgkin-Huxley mechanism that's associated with the segment that contains the 0.2 location on the apical. So I can read that, I can set that. And so forth. And I can, different segments can have different variables in general, unless you're using globals, but there was a discussion on Ask Tutors about globals a while ago. Yeah, I think we've already talked about temperature and nseg. I don't know why this slide's on there. If I do want to loop over, if I want to set all of the segments within an apical to be the same variable, well, I could just loop over all the segments. If I do some sort of calculation based on the segment location, I can do that here as well, right? That might be the real case where I want to loop over something instead of just assigning it to the section. I can loop over all of my sections using for sec and h.allsec. Remember, h.allsec is our, it's not technically a list, but it's effectively a list of all of the sections in our model. If I have a specific, section, let me see if I have, okay, so going back here, I have, so main, remember when I did the topology, what do I have? I have a thing called main, it's got a dind1 and a dind2, and let's say that I have somebody else, and it'll be a thing called soma, and it's gonna have the name of soma. And now if I look at the topology, I'll see that I have two top level things, the main and then the soma. And then once I have, if I have any section at all on a cell, so let's say the main, I can ask for the whole tree is what it's called. And it's everything that's attached to the main. And so this is going to give me main, it's going to give me dind2, and it's going to give me 1. It doesn't give me soma because soma is not attached to main. in this particular case. And soma.wholeTree, well, nobody's attached to soma, so it's just the soma. So it's often, and I would actually suggest that it's probably better to think in terms of cells rather than thinking in terms of all of the sections, but you'll find lots of code that works with all of the sections in one go. The other interesting thing that you see happening here is as I'm looping over this, I'm applying some function of distance, and I can measure the distance between 2 points using h.distance. So if I pass in the distance, h.distance between whatever segment I have and the center of the soma, it's going to tell me, well, how far, I'm sorry, those are I'm sorry. h.distance measures the distance between two segments or two, well, let's just say segments for now, but there are other things that you can pass in there. So this is going to say the distance between the center of this segment and the center of the segment containing soma of 0.5. And that's in real distance in microns. And so you could imagine that conductances might be functions of distance. So this happens, for example, in pyramidal cells. I believe A currents are functions of distance from the soma as a rough approximation. And you can use list comprehensions to grab a whole bunch of parameters at once and turn them into a list. All right, so we're almost there. We've described, I've been talking a lot, but we've described our model, our structure. We've connected a bunch of things. We've inserted ion channels. We've added maybe a current clamp to get everything going. But in order to actually see what's going to happen, well, we've seen we can look at shape plots and all of that, but maybe I want to just look at what's going to happen at a specific point. So if I want to actually record what's happening, well, I can construct what's known as a vector. It's a vector that's going to record something. So I'll construct a vector. It'll record a specific location's, let's say, membrane potential. And remember, so normally I'd say like axon of 0.5.v for the current membrane, for the membrane potential at the center of the axon, but that's just a number. If I want to record that location over time, I'm going to need to include that underbar ref underbar. And we're just going to see that if you're doing a record, there better be an underbar ref underbar. But so I'm going to record the voltage potential as it changes at the X location on the axon. I'm going to also record time into a vector because if I don't know what times the values correspond to, knowing the values is not super helpful. Fair? So this is one type of thing, and I can record voltage, I can record concentrations, I can record currents, and it's all just a question of whatever you pass in here at the very end. I can record state variables in general. I might also, okay, so I've been talking a lot. So before I go on, any questions on anything that I've said? Because I can't see faces or anything. If I'm making any sense. Okay. All right, so the other type of recording that you probably are going to want to do is you may want to record spike times. And so I'm not going to go into it too much right now until we talk about networks. But if I want to record spike times, I'll construct a vector again. I will think of this as a recipe right now. Fundamentally, I'm going to create this object called a netcon. It's used for connecting networks, hence the name. But in any case, I can monitor one specific location. So axon 0.1 segment, membrane potential. And then I need to pass in this extra keyword argument, just identifying the section that's associated for technical reasons. But in any case, if I follow this architecture, I construct this netcon with a location that I want to monitor. And then I just want to see when it crosses a given threshold. So I'll set nc.threshold to be 0 millivolts, where millivolts here I got from neuron.units. And then I can just record every time that it crosses this threshold from below in spike times. So every time I go up above 0 millivolts, I'll consider that a spike time. And if I don't hit 0 millivolts, well, then I'll consider that a failed attempt at a spike. And so I can use this to build data for like raster plots of when my cell fired. And if you think about it, you can actually be reasonably clever, and you can use this to think about, well, how you can record times of wave propagation. You know, how long, when did the action potential hit here? When did the action potential hit here? And then distances rate over time. So you can calculate the speed of an action potential propagation, or the speed of a calcium wave, or the speed of any of a number of things using this kind of an infrastructure. All right, so we can record a time series using an underbar ref in this syntax. We can record spike times, or really event times, because we're not limited to spikes, using a netcon. All right, so now we can get some readouts of our model. The only other things that we need to do is we need to make the model go. And there's a number of ways that you can make a model go. We can just set a specific value. Like if I set the membrane potential of the center of the soma above threshold, well, maybe in my model, that'll be enough to, well, fire an action. Well, I guess by definition, it's above threshold. It'll fire an action potential, and it will, and I'll be able to see something happen. I can use a voltage clamp. There is an SE clamp, which is a single electrode voltage clamp. There's a V clamp, which is a 2 electrode voltage clamp. And if you know anything about how these things work, they're not instantaneous. There's wires, they have resistance, and this has some sort of implications for all of this. But if you don't, let's just think of this as I have a voltage clamp where I'm going to force it to be -65 millivolts until time 10 milliseconds, and then I'll set another amplitude and another duration and another amplitude and another duration. And I can use this to voltage clamp voltage clamp my cell and see how it responds to that. I can inject current using an I clamp. I can use synaptic inputs using a net stem coupled with some sort of synapse model. Again, you can find a gazillion of these on Model DB, but Neuron comes with simple ones like an exponentially decaying synapse. So this is a synapse that occurs at the center of the soma with a certain time constant and reversal potential. And obviously the reversal potential is going to decide whether or not it's going to be excitatory or inhibitory. All right, so now I can record my model. I can make it go. I can define everything. So let's actually run the simulation. So this is the full setup. So if I want to actually run the simulation, I've already said we're going to start every code file with this load file of stdrun.hoke, just to make it go. I'm going to need to initialize my simulation. And so the simplest initialization that you can do, and we'll talk about more complicated initializations next week, but the simplest initialization that you can do is to assume that it's a constant membrane potential everywhere. So I do h.f initialize, and then I pass in my membrane potential that I want to initialize to, so -65 millivolts. And then I can run this until a specific time using continue run. So this will run until time 10 milliseconds. If I'm already at 10 milliseconds or past 10 milliseconds, it will do nothing because I'm already at or past 10 milliseconds. So this is how much, this is the time that you want it to stop running. You could also force it to advance one's time step at a time using f-advance instead of continue run. In that case, you don't even need stdrun.hoke. We'll talk later about numerical methods, and when we talk about numerical methods, there are various things that you can do to improve numerical accuracy. But just want to highlight that here so that you see this. Variable time steps, you could use that. You could use smaller fixed time steps. You could specify error tolerances. You could increase the number of segments. And again, we're going to talk about all of that and the implications thereof when we get to the numerical method slide. So with that, I'm going to stop with the background introduction and switch to a demo. But before I do this, does anybody have any questions? All right, so let's see how I would go about. Let me create a new window. So here's what I would do. So here is my lovely text editor. It's VS Code. I'm going to try and get a cell to fire an action potential. And I think if we can do that, and we can see that action potential, we're in good shape for the homework. So let's go up. I'll start a new file. I will, let's see, go ahead and save it. I've been working, here's my files for the day. And this will be action potential.py, let's say. Traditional Python extension is .py. Ugh, okay. Sorry, I just reset this up and it's, let's see. Hold on, I just want to see one thing. Okay, we're good. All right, so I just reset this up, so there's minor difficulties. So, okay, so I've created my file. Every time that I want to run a neuron simulation, remember there are 2 lines that I said that I'm probably always going to want. Anybody remember what they are?
Import.
Yeah, I'm going to need to import something. What am I going to need to import?
Import from Neuron import H and GUI.
From Neuron import H. I'm actually going to pass on the GUI right now because I don't need it for this example. Yeah, I'm going to actually, you know what? I'm going to go ahead. You're right. I'm going to go ahead and add the GUI for now. So let's say I've done that. From Neuron import H, GUI.
Then you need the load file statement for standard.
I can do h.st load file standard run.hook. I actually, technically speaking, fun fact, I don't need to do this explicit load file if I load the GUI, because if I load the GUI, I already have all of the standard run controls. But since I might not want the GUI in the future, it's probably good practice to go ahead and leave it in here. All right, I want to create something that's going to do an action potential. So in order to have an action potential, I'm going to have to put it somewhere, right? So what do we need in Neuron? What's the thing that we put somewhere?
Section.
Right, I'm going to need some kind of section. So should we call it the axon? Let's call it the axon. I'm going to create an axon. It's going to, which is a section. It's going to have a name of axon. And you know what? Here's what I can do. I just saved this. I'm going to go ahead and pull up my terminal here and switch into my folder. Cool. So here we are. I'm in my folder. If I do an ls, I see it. So what I can do actually right now is I can go ahead and run Python. If I give us this -i flag, it makes it interactive, so it doesn't shut down when it's over. And I can run the action potential.py file. And so sure enough, when I run it, it pops up the graphical tool, the graphical interface. And I have, and so we think I've created a thing called axon. Well, let's find out. I can do a topology, h.topology, Sure enough, I have an axon. And the
Could you
reason that
repeat?
yeah, go ahead.
Sorry, could you repeat about the interactive thing? I missed that.
Oh, I just meant that this thing pops up. The graphical window pops up. Oh, sorry. Okay.
Yeah.
Got it. So if I just say Python action potential, what Python by itself is going to do is it's going to run the script, and then when it's done with the script, it ends. Right? So it's going to run everything in action potential. I know that's because I had this other guy around from before. Let's try this again. It's going to run everything in action potential. You see, you may have noticed it flickered a little bit. There was a delay, but then it came back. So I can't do anything. I can't test it. I can't see if I've made any mistakes. Well, this will tell me if I made 8-bit mistake, right? If this code is complete nonsense, if I made an error here, like let's say that I misspelled section because I miscounted the number of T's in section. Well, now let's see what happens. Now, if I run this, I get an error, right? So I do learn something here, right? So it says, what does my error say? In line 4, I'm talking about, which is this line, I'm using this thing called section with 2 T's, but there is no such thing. Right, so Python is going to be very helpful. It's going to give us this hint that maybe we don't want to do this. There's something wrong with our spelling here. And sure enough, if I fix this, I said if I fix it, not make it worse. If I fix it and run it, there's no error, but I can't test it. I can't interactively explore it. So now, if instead I do Python space -i, this is the interactive bit, it doesn't stop when it's done. It drops me into this interactive terminal. Do I have an axon? Well, sure enough, I do. Do I have it? Is the topology right? Well, sure enough, the topology is right. There's, I can use the graphical tools. There's this thing called model view. It'll tell me that, hey, look, I have an axon. Yay.
Okay, thanks.
Yeah, so that's what the interactive thing does. It lets me test to make sure that I didn't make mistakes. All right. So I've got my axon. I wanted to fire an action potential. What am I going to need in order for this axon to fire an action potential?
We need to insert the active channels.
Yeah, I'm going to need some ion channels. So h.hh, and I'll insert those into the axon. Okay, and I'll save this. I'll run this interactive mode again, and I'll show you another little secret here. Okay, didn't get any errors. That's always a good sign. Well, yeah, it's a sign. So in any case, I have this thing called the axon. If I look at, let's do this. Let's look at the dir of axon is 0.5. So if I have a specific segment, what's in the directory? What's there? Well, there's a whole bunch of things that I could ask about. I could ask about the area. I could ask about the membrane capacitance. I could ask about the diameter. Look at this. Hodgkin-Huxley. I can ask about Hodgkin-Huxley. That looks promising. You know what else I can do? So that suggests, at least, that I've successfully inserted Hodgkin-Huxley. The other thing that I can do is I can take my section and I can do a .p section. And p section says basically print the properties of the section. And if I do that, well, I get this nasty sort of dictionary. But in particular, I do see that there are density mechanisms that are involved, and Hodgkin-Huxley is one of them. And by the way, the other fun fact here is if I do this import pprint, I can do pprint.pprint of the same thing. Pprint is pretty print. So it's like printing, but it's going to make it all pretty. What does that mean? There we go. So it's going to give me a nice little indentation. Makes it easier to read. So here I see that my axon has a bunch of properties that I print out, including a density mechanisms that include Hodgkin-Huxley. And here's the reversal potential for the leak. Here's the conductances. Here's the state variables, and so forth.
I have a question.
Yeah.
if you could scroll up, when you did the directory on axon,
Yeah.
down there we observe there's potassium ion and sodium ion. Those are now available because we inserted HH, or by default in Neuron, if you create a section, ions are inserted.
I claim this is a question we can experiment and find out. How do we experiment to find out?
I mean, without inserting the HH, we could just look at here.
Yeah, let's create a new section. So here's a dendrite, and I haven't inserted the HH. So now if I do the dir of a segment on the dendrite, so I don't have an HH.
Yeah.
Okay. And in particular, I also don't get a sodium ion and a potassium ion.
Yeah, makes sense. Thanks.
Yeah. All right. Okay, so I have an axon. I've inserted a Hodgkin-Huxley channels. Actually, you know what? Let's just rerun this. And here's an example of the advantage of having the graphical tool available here. So now that I've inserted a thing, I can still do, let's do a graph. All of this stuff that you learned with Ted still works. I can still pop up a run control. I can still make a voltage axis. I can still init and run. Of course, nothing happened. Why did nothing happen?
No stimulus.
There's no stimulus. Yeah, so I'm going to need to add a stimulus. And I could do this from the graphical tools, but the whole point of this is to do this from scripting. So let's just get out of this for the moment. Oh, by the way, I'm hitting Control. Well, you already know how to do this because you've been doing this all the time, but I hit Control D to get out of there. You can also type print. So if I want to create a current clamp from the command line, from the programming side, it's going to be, I'm going to create an h.i clamp. I'm going to put it somewhere. So it's going to live at the center of the axon, let's say. Or, well, let's put it at towards the beginning of the axon. Actually, you know what? Let's put it exactly at the beginning of the axon. And that current clamp is going to have a certain delay. I'm going to want it to start at time, let's say 2. And since I didn't import units, I'll just say milliseconds. It's going to have a certain duration. I don't know. How long is a good time to inject current for? Well, let's do an experiment. We'll inject current for 0.1 milliseconds, and we'll need to specify an amplitude. And so I don't know, as good as 1 is always a nice number to play around with. It's a lot of current, but we're not going to kill any cells, so that's fine. And actually, it's going to end up, we'll see this is actually not going to end up as strong of an effect as you might think. So if I take this, I go back, I can rerun this. I could pull up my, I said I could pull up my voltage axis. I could pull up my run control. Yeah, go ahead.
Second. When you pull up the voltage axis, you had last declared the dendrite, right? So the voltage right now, that V.5, won't it be the dendrite's voltage that will be plotted or not?
Okay, so it's not for 2 reasons. First of all, the default thing is actually not the last one that's created, it's the first one that's created.
Okay.
Secondly, that was not part of my script, right? So when I exited and relaunched, right? Because here I've just relaunched and I've ran
correct,
whatever.
correct.
So den doesn't exist.
Yeah,
And
yeah,
we could confirm that with the topology if we wanted. It's just the axon. All right. So now if I were to, well, actually, let's just show what happens. So we can do this programmatically. So we initialize the simulation. So I can initialize this to -65 millivolts. And I can continue run this until time 5 milliseconds, because that's how long my graph axis is. And if I do that, I see the line plots across my graph, but it still looks sad. Why is that? Anybody know? Well, let's do a view equals plot. So we see that at time 2 milliseconds, we do get that bump, but it's not enough. And why is 1 nanoamp not enough? For 0.1 milliseconds, not enough to get the cell to fire?
Because it has the huge diameter.
Yeah, it's got a huge diameter. All right. So let's change it. Let's say I change the amplitude to 10. IC.amp is 10. Let's just run this again. Still no good.
Because we are doing that in the edge, not in the center of the axon. It's at the end of the axon.
I don't think that matters here, because there's nowhere for the there's nowhere for the current to go.
Yeah, that shouldn't matter, yes.
If it was connected to something, then I'd agree with you. Oh, actually, you know what? That is an interesting point, though. So let's go on to this. Let's suppose that instead I set inseg, because I haven't specified inseg. Let's say that I set inseg to 101. Now let's see if that makes any difference. I didn't initialize this. It did not make a useful difference. Never mind. Okay, so what do? Well, I could hit it larger. There we go. I got an action potential. You see that? Not anymore, I guess. Right, so I could initialize. So what did I do? I set it to 1,000, and then I've defined it, and I run it, and then there we go. So let's just go ahead and do that. So we found that an amplitude of 1,000 nanoamps for 0.1 milliseconds with our default size is sufficient to get this to fire. And then we can check to make sure, now that we've saved this, by popping up our voltage axis. I said by popping up our voltage axis, initializing and running, and sure enough, there we are. So we've gotten back, we have a description of the model that's procedural, it's programmatic, and we've gotten back and we're able to generate an action potential. We're hitting it quite hard, but that's okay for now. All right, so I'm also very conscious of the time and the fact that we started late and are now over. So I'm trying to figure out what so how about this? So that for the people who have to run, what I'd like to do is I'd like to get this to the point of being a graph that we can actually display and look at, where it just runs and we see the simulation. But I understand that people have to go. So let me just move forward. The last 3 slides of all of this are 3 exercises that I'd like to talk about on Tuesday. So I'd like to encourage you to look at these. So here, so what I'm trying to do right now is to plot the action potential as a function of time. The other way that you can look at an action potential, though, is how does the membrane potential vary with space? And so for this exercise, I encourage you to use to make a plot of the membrane potential across space at several different time points. And if you pick reasonable choices of axon size and current clamp injections, you ought to be able to visualize a propagating wave. This is what the membrane potential pattern looks like here. This is what it looks like there. And it's not going to look quite the same thing as an action potential against membrane potential versus time, right? Time and position are different. The next thing I encourage you to do with this is to look at the axial resistivity. Remember in squid and therefore in neuron by default, 35.4 is a reasonable resistivity. Mammals, it's more like 100. So how would that one simple change affect the wave propagation? So it's a one-line change. You can rerun your code. You'll get a new figure. We'll see how it goes. For a second exercise that I want to talk about on Tuesday, do the same thing, but sort of voltage clamp it instead. So don't use a current clamp. Use a voltage clamp and measure the amount of, with Hodgkin-Huxley, doing the voltage clamps at various step clamps, and see what you get in terms of the amount of potassium current. What about sodium current? How does they evolve over time for a given voltage? And so you can plot that and you can look at this. So here's when I did it at various voltages. I found that the potassium current looked like this. So it ramps up slowly, almost like a sigmoid, and then it levels off until such time as I release the voltage clamp, at which point the current decays, but it's not instantaneous. And then I encourage you to look at the potassium concentration. So if the current is doing this, what's happening to the potassium concentration over time using the Hodgkin-Huxley kinetics? And it may, depending on how you thought about this, the answer may surprise you. And then we need to think about what that means in terms of, well, we'll think about what that means on Tuesday and why you see what you see. And finally, I suggest that you use an action potential in a long axon and measure the wave speed. And you should be able to see that the wave speed is going to be constant as long as you're away from the end conditions, but near the ends, it's not going to be constant, and that might be worth thinking about. And then what kind of a change in morphology would explain a wave speed that looks like the red line instead of the blue line? So something happens. I've changed the morphology in my model to get the red line for the wave speed. So those are the exercises. Anybody have any questions on the exercises for Tuesday? And I claim everything that you need to know to do this is in this slide deck. So for those who want, so if there's no questions, for those who want, and for anybody who can watches this video later, I'll go ahead and complete what I was doing to get to the point where we have we're able to make a propagating action. We're able to make an action potential, and we're able to look at the time series of the action potential. For anybody else, I thank you for putting up with our interesting challenge of today, and I will see the rest of you on Tuesday. All right. So just to continue my walkthrough for anybody who's watching now, and I see several of you are, so thank you for hanging out with us. So we've created our axon. We've defined our stimulus, which is going to be a current clamp. We know that we can run it for h.f initialize of -65. And actually, I am going to use units because I do really like units. So from neuron.units, import millivolts and milliseconds, because I think it makes it a lot easier to read and a lot less mysterious. So I'm going to initialize my model to -65 millivolts, and I'm going to continue run this until 5 milliseconds. And if I do that, and I just run it, cool. But that's not very helpful because I don't actually see anything. If I were to look at the voltage axis, I'd still not see anything. Why? Because I only created this voltage axis after the simulation was run. So there's nothing to see here. I'd have to rerun the simulation from the beginning if I wanted to see it. Alternatively, and we've seen that, we've done this many a time, and we've seen this. F initialized -65, H I continue run to 5 milliseconds. Cool, there's our action potential. Nope, I said, there's our action potential. But if I want to actually record these values and see them, I'm going to need to create vectors. So let's do that. I'm going to get out of that. I'm going to go back here. And any vectors that I want to do any recording have to be defined before I initialize the simulation. I encourage you to begin by always recording time, because if you don't record time, again, it's not self-evident what any of the values correspond to when these things happen, especially if you're using what's known as a variable step integration, which we'll talk about more later. So if I want to record the time, I'll create a new vector, and I'll just do a dot record on that vector, and then I'll record h._ref_t. Why that? Because h.t is the current time, and then we put the _ref_ to indicate the concept of time, the pointer for time. And if I want to record the voltage, I'll do the same thing for voltage. I'll record a specific location, let's say the center of the somas. Well, if it was just the membrane potential, it would be .v. But if I want to record it, that's the current membrane potential. But if I want to record something that changes, I'm going to do _ref_v. And so now if I run this, okay, again, it didn't plot anything, but if I were to look at t as a list, which I can do as list of t, well, I get a whole bunch of times, and I can look at v as a list, and I get a whole bunch of membrane potentials. Yeah, so I get a whole bunch of times and a whole bunch of membrane potentials. I can do anything with these that I want. I don't even have to convert them to a list, honestly, for pretty much any purpose, except printing them out. So like if I print out t, it just shows up as vector 3, and v shows up as vector 4, which means sort of nothing. But now these are numbers. If I can throw them in a database, I can plot them. So if you know matplotlib, so matplotlib.pyplot as plt. I gave you instructions for plotly, so this is a different one, which I'm doing mostly just because I think more people are familiar with matplotlib than plotly. So I can load in my graphics library pyplot, and then I can just do plt.plot, and I'll just feed it my t and my v values. And then I'll just do plt.show. Nope, not slow. Show. And it did it on a different screen, so I'm going to drag it over. But sure enough, right, all of my graphics functions are going to pop up in a regular, in this case, matplotlib window. I can zoom, I can save, I can do all of the things that you expect to be able to do in a Python window because it's a Python window. It's a regular Python graphics window. So let's go ahead and add that to our file so that it runs automatically. So I'm going to say that I'm going to want to import matplotlib.plotly as plt. It's just a convention. And then I'll just do down at the end, after I've initialized and ran my simulation, I'll plot it, t comma v, and I'll show it. And now actually, fun fact, I don't need the -i because the show it is going to cause it to wait. And in fact, since I'm making graphics, I'm going to just go ahead and get rid of the GUI as well. So now if I run python action potential.py, Oh, goodness. Not Plotly, PyPlot. But so you'll notice, first of all, you'll notice it changed color when I did that. And also you'll notice that I got an error message. No module named matplotlib.plotly. Why? Because I made a typo. But also the other thing that I want you to take away from this is if you make a mistake, it's okay, and it'll tell you what you did wrong. Read the error messages that you get. So now if I run this, it pops up the window, and it waits for me to close it before it returns the command prompt. So now we're able to, now we have a thing, it's a reproducible code. I can give it to anybody else. It should give the exact same results on your computer as my computer. We can encapsulate this inside of a cell object and make many of these, but I think that may have to wait. In the interest of time, I think that can wait till next week. But in any case, yeah, so there we go. So working together, we've reasoned through, we've thought through how we create a code that's going to generate an action potential. I understand that this may seem more complicated than doing it with the GUI. And I think sometimes for simple models like this, that's going to be the case. But when you start doing more complicated things, you know, we're not doing any loops, we're not doing any systematic parameter searches. You'll find that writing in code is going to make your life a lot easier. But you'll notice that even as I did this, even as I was writing in code, I did take advantage of the GUI to let me check, make sure that I was doing the right thing. And my advice to you, I don't think, if I was doing this by myself, without there being an audience, I would probably have done larger chunks and taken bigger steps, but I would absolutely still break this down. I would do little itty bitty pieces that were taking me a little step further, a little bit closer to what I wanted, because none of this takes very long, right? So I'll do something that'll take me a little bit of a step there. I'll make sure that it works before I go back to change this. This is going to be especially important when you're thinking about network models, right? Your network's not going to make any sense if your cells don't make sense. So make sure that your cells make sense before you are doing the right thing, before you look at network models. So you build up each one of these things, every level of complexity, test it, test it, test it, to make sure you're getting reasonable results. Yeah, so that's my overview on this. Like I said, next time we'll look at doing some of this. We'll look at more complicated initializations. We'll look at more stuff with maybe concentrations and networks. We'll look at morphologies the following week. So lots of fun stuff coming up. But I think that's going to end for today. So again, I thank everybody for the patience with our initial chaos. And if there's any questions, I'll hang out for a little bit. Otherwise, I'll see you on Tuesday. Thanks all.
Thanks.